My name is Joe. I'm going to talk about 3 unresolved, in italics, problems in studies of the circumgalactic medium. So, before I get started, I thought it might just be useful to talk a little bit about my faith, particularly in the context of galaxy formation. This is something that we don't often do. Perhaps this would be a useful discussion topic, as we could just talk about how we feel about things, or what exactly we do or don't believe in. And so it's partly motivated by the fact that I was just notified that I got tenure. I just want to let you all know now in a public forum that you might want to hold your applause now. So I actually don't believe in AGN feedback. So I could get into that. The details of that would be a different talk, more like a rant. Perhaps that'd be more appropriate over drinks. But I believe that there are certain cases where it's taking place. I believe that there are outflows. I believe that in some situations bubbles are being blown, etc. But I don't think that this is sort of this panacea that solves all our problems in galaxy formation. And so one of the things is when you come out as an AGN feedback denier, you sometimes get a little bit ostracized or labeled, or people don't pay attention to you, or they don't take you seriously. And so, I just want to make it clear that I do believe in climate change, okay? All right? I believe that human activity over the past century has caused a raise in the Earth's atmosphere. But let me go a little bit more into why I'm trying to be so provocative here. Okay, so it's usually assumed that the physical state of material, that is diffuse gas, the circumgalactic medium, which is falling onto galaxies, is correctly captured, resolved by our hydrodynamical simulations, okay? That the input, the infall, the material coming in is correct. And then, lo and behold, the galaxies are too massive, right? And then we have to play some games to try to fix that problem, right? So one question is, has this really been tested, right? That this is actually the physical picture of how gas gets into galaxies. That's number one, right? We assume that the flow of gas in the galaxies can be predicted ab initio. Has that been tested? Are we really sure that we resolve that? I stole these beautiful slides from Freke van der Voort's talk, by the way. These are the OWL simulations that you're looking at. And then, I might eventually be convinced or be able to concede that something like AGN or supernova feedback can actually redistribute or change the state of this diffuse gas in the circumgalactic medium. And imagine we're looking here at a galaxy redshift 2, and if you do that, right, if you put that gas into the circumgalactic medium in the wrong physical state, or if you're not actually capturing how those outflows interact with the circumgalactic medium, then you have a problem. The initial conditions for galaxy formation are now wrong, and I have no reason to really believe what happens 10 gigayears later, right? It's very important. There's a lot of fuel in this medium that could or could not form stars, and that's going to depend on the physical state of gas in that medium. And so that's, where I'm pushing you here is maybe there are physical processes that we're not resolved, and I'm going to show you 3 examples from observations of the circumgalactic medium where I claim that there's a severe conflict with our current picture understanding. Okay, so how does this work? Probably people are familiar with this, and I wasted a lot of time on that rant. So the idea here is that you find a background source, a bright background source, i.e. a quasar, within the virial radius of a foreground galaxy. Okay, and the reason why you want to play these games in absorption is because it's really hard to detect this material in emission, but using absorption lines you can detect gas all the way down to the mean density of the universe. You have 10 orders of magnitude of dynamic range, and pretty good dynamic range in temperature. Okay, so we can't detect 10 to the 7K plasma. That would require X-ray lines, of course, but we can go up to 10 to the 6, and we can go down to arbitrarily cold temperatures. And so then, sort of what we can and can't measure, just to make it clear, if you have low resolution data, so moderate resolution, then you can say something about kinematics and covering factors, but you can't really say very much about physical properties. So, just be warned, when people use low quality data to make claims about physical properties, they're usually making lots of assumptions that you should be skeptical of. Now, the first part of my talk is going to be focused on what you can do with really exquisite data, okay, i.e. shell data with high signal to noise. And then you can start to get at what's the enrichment of the gas, are there multiple phases, and this is really important, right? Gas masses, cloud sizes, cloud densities, this is all then a check on what people are doing or simulating, right? And if it's a powerful test because I can actually measure the density of gas in the circumgalactic medium, and if that disagrees with your simulation, then we might need to rethink how those work. Okay, so bright quasar here, what we do is we take images of quasars that have existing Echelle data, then we don't have to go and get that extra Echelle data. So this is like one of the brightest quasars on the sky. Okay, we go and get deep images. Okay, this is very expensive. Just the imaging costs 4 hours on an 8 meter, and then you got to get the spectroscopy to find galaxies. That costs another two hours. Now MUSE, an instrument that's coming along on the VLT, will revolutionize this because you can do everything in one shot. But then, so we find here a low mass galaxy, and I realize that this is not a meeting about low mass galaxies, but the point is basically the same. Okay, a Lyman alpha emitter at redshift 2.5 in the foreground of that quasar. Okay, so there are some stats on the galaxy. It's pretty puny. This is the first time that anyone's actually studied a galaxy that's this low a mass in absorption. Okay, and so this quasar has 5/9 of total integration on it, on the VLT, with a spectral signal to noise per pixel of 70. And so then you have all of these ionic transitions, which represent absorption lines. So there is a so-called Lyman limit system at the location of the galaxy, and you're looking at metal line transitions relative to the systemic frame of that galaxy. So 0 is where the galaxy is, all right? Every component that you see here is a metal line absorber, and we have 13 different transitions that we can use to construct a very detailed physical model of what's going on in that gas. And so I'm going to zoom in here on just a couple of these transitions. So now I'm looking at a couple low ion ionization states, so carbon, singly ionized magnesium. Here's carbon triply ionized, it's a doublet, and then we go all the way down the Lyman series, all the way down to Lyman 12. And so what you notice is that at each location of a turbulent component, that's how we fit these lines. We identify the metal line components, okay? Right? I can totally reproduce all of the hydrogen just via thermal broadening, okay? That tells me, and this is very powerful, that the metals in the gas are very, very well mixed, okay? They're definitely co-spatial, because if they weren't on the same spatial scale, if the metals were on a really small scale and the hydrogen was on a really large scale, then you would see differences in the kinematics, and we don't see that. And this is something that you can only really see if you go down to Lyman 12 with this kind of signal to noise. And that'll become important later, okay? So then, we use Cloudy, okay? And we've wrapped Cloudy around the Markov chain Monte Carlo engine, which allows us to then make precise statements, quote realistic error bars. So these are the ions that we measure. The red curves show various draws from our posterior for the best fit photoionization model. Photoionization does a very good job of describing this data, as you can see there. Okay? And then we measure physical parameters with convincing error bars that represent marginalizing over things like the unknown shape of the UV background, etc. Okay, so you don't have to believe that much here besides atomic physics. Okay, the gas is essentially very nearly optically thin. So geometry, radiative transfer effects, not a big problem. Cloudy slab approximation is perfectly appropriate for such a system. Okay, so if you believe in atomic physics, then you should believe that we've determined these cloud parameters correctly. Okay, so then now I can take this absorption line system and I can dissect it as a function of velocity. So the first thing you notice is that the velocities are pretty big. 400 kilometer a second motions around a low mass galaxy. Okay, so that means, and that the gas is very highly enriched. Okay, so 0.2 to 0.6 solar already at redshift 2, that's the typical enrichment level of the center of a star-forming galaxy, right? So this looks like a pretty good candidate for maybe something like feedback or an outflow from this low-mass galaxy. Perhaps, some kind of wind is being powered here. Now, what's very troubling, is, so now I'm showing you in each component physical properties. And so look at what the cloud sizes are. The cloud sizes are 100 to 400 parsecs, okay? And the typical cloud mass is 200 to 5 times 10 to the 4 solar masses. So that's really, really small scale structure that you're seeing in the circumgalactic medium. And just for those of you that may be experts, uncertainties in the radiation field that goes into our cloudy model are essentially not at all an issue here. That would only lead to larger cloud densities, smaller clouds, less massive clouds. Okay, so this is all very robust. You only need to believe atomic physics and that we basically know the level of the UV background, which we do very well from the Lyman alpha forest. Okay, so now keep in mind, this is not some shitty weather in the outskirts of a galaxy that you shouldn't give a shit about, all right? I mean, this is the CGM. This is what it looks like. The total mass is, of course, independent of the cloud size. The clouds have a low volume filling factor, but they still, in aggregate, create a large covering factor and a large total mass. So this is a low mass galaxy, so the mass may not seem that large, but this is 60% of the total stellar mass of that galaxy we estimate. So this is what the CGM looks like. Now I'm only showing you a detailed model of one system, so that caveat is in play. Okay, so where am I going with this?
How do you estimate the covering fraction for one line of sight?
Well, we estimate it statistically from a population of such galaxies, and then the fact that you intersect multiple such clouds, right, along the line of sight also suggests that it's about order unity. But that's a fair question. They may not all, not all galaxies may have a covering factor of clouds that look like this. Okay, so where am I going with this? So you've probably seen this before. This is the so-called blob test that's used to validate whether simulations are resolving the interaction between hot and cold phases. And so, this is a very old result that if you have a cold cloud moving through a hot medium, it's moving at Mach 10 relative to its own sound speed, moving at about Mach 1 relative to the sound speed of that medium, then you basically disrupt this cloud in about 5 cloud crushing timescales, okay? And if you put in numbers here, then you get that these clouds should be basically ablated in 10 to the 7 years, okay? The dynamical time of this galaxy is 10 to the 8 years, okay? So, do current simulations resolve this process, this interaction between clumpy, small-scale, cold structures and a hot plasma, which is essentially ubiquitously predicted to be there? Now, I had to assume what the hot plasma density is. This is the only thing that I don't measure. However, I'm only sensitive to the square root of the uncertainty in that hot gas density. I think there has to be some hot gas there, okay? So, sadly, not even close, all right? So if I were to be extremely aggressive and require only 3 resolution elements across this cloud, that would be 7,000 SPH particles. The image that you're looking at there has 128,000 SPH particles in it. That's why it looks so pretty. If you under-resolve the cloud, you don't capture the disruption and cold gas lives for too long, perhaps leading to too much star formation. I don't know, okay?
No, that image contains 0 SPH particles.
Well, this is the grid run, but when people run this with souped up SPH and they claim that they want to get it right, then they need to have 7 resolution elements across the cloud. Fair enough. That's the AMR run. Okay. All right. So if you want to do this with AMR, you need 100 parsecs resolution, but in the circumgalactic medium. That's essentially never achieved. Okay. And even the highest resolution zoom-in simulations are not even coming close to what you would need, which is 3 solar masses. You need 1,000 times more particles, right? So this really sucks, okay? Like, this is bad news for simulations if the CGM really looks like this. And I claim that we've seen this small-scale structure issue before. Maybe we just chose to ignore it, or maybe we didn't think it was such a big deal because we weren't seeing it near galaxies. But Michael Rauch showed that there's 30 parsec structure scale in quasar absorption line systems. Of course, there's no galaxy necessarily here. Xavier and I, Prochaska and I analyzed a similar system, but in a much more massive halo around a quasar, and we also got very small sizes and high densities. Yoke wrote a very provocative and thoughtful paper on small-scale structure in carbon-4 absorbers several years ago, and we see very small-scale structure in high-velocity clouds. Okay, so at this point, you might be pretty bummed, and perhaps, even in denial, but I haven't shown this yet, because this analysis is very expensive, but the entire circumgalactic medium could be in 300 parsec clumps, okay? I've shown you a single analysis, and I think that we could continue to do this, but it's hard. Okay, so right now you might be thinking that the CGM is just, that you might be denying this and not want to realize that maybe the simulations need to be rethought. But I saw some great talks here at the meeting. My 2 favorite talks so far were Yuval Birnbaum's talk, where he was talking about resolving Kelvin-Helmholtz instabilities in cold streams, and Brian O'Shea gave a nice talk about thermal instabilities and fragmentation in the context of the ICM, and Jay Gallagher just showed us an example of a case where that might actually be happening. So I think there is hope, but I think we need to start thinking about circumgalactic quenching. Okay, you can put that on your list, Frank, as my mechanism that hopefully that will catch on, maybe not. Okay, all right. So now we're going to move up to more massive halos. This is problem number 2. And I'm going to use quasars to trace massive halos at redshift 2. So 10 to the 12.5 solar masses is the mass scale. That's about 6 times larger than the mass scale of an LBG. Okay? And the reason why I'm going to use quasars is because they are the progenitors of your local quenched galaxies. So you're going to get a snapshot of what a massive elliptical looks like at redshift 2. And also because it's just easy to do, because I don't have to do very deep imaging to find them. I can find 1 million of them in the Sloan Digital Sky Survey and then mine that data for these very rare pairs. Now, there's of course the issue that the quasars are not representative objects. Maybe for this conference you don't care because they definitely evolve into ellipticals. Okay, and so they have to look like ellipticals at some later time given their mass. But there's some results from Herschel and also C. Knut Janke's talk yesterday that basically indicate that quasars lie on the star-forming main sequence. Okay, so what we do is the same game, but now with lower quality data because quasars are faint. Okay, so background quasar there, foreground quasar here. This is the Lyman alpha line. Lo and behold, in this pair, which has an impact parameter of 140 kpc, there's a damp Lyman alpha absorber at the foreground quasar redshift. Here's another example with a strong Lyman limit system at the quasar redshift. How often does that happen? Well, here it is. Okay. So on the upper panel, you see a data point for every pair in our sample where the foreground redshift is being shown and also the impact parameter. If I've been, filled symbols have a strong absorber or a so-called Lyman limit system. The open ones do not. Okay. If I bin that up and take the fraction of the filled symbols to the total, then I basically get the cool gas covering factor in the circumgalactic medium of these quasars. Okay. And so that covering factor is startlingly high. 60%, okay, within the virial radius. And if you just look at the nature of that absorption, then we deduce that the CGM is dominated by a cool metal and massive, so about 10 to the 10, or that's a lower limit, 10 to the 10 solar masses, and there are definitely metals in this gas. All right, so then this has been done before by Yop's group and various others, but what you do is you run zoom-in simulations. The reason why you want to run zoom-in simulations is because I would argue that you want to resolve the CGM as best that you can with current technology. Okay, the feedback in these simulations is not strong. It's just star formation feedback. There is no AGN feedback. Then you do ionizing radiative transfer and post-processing. That allows you to construct an H1 column density map and essentially exactly reproduce the observations that I just showed you. And so the bottom line is when we do that, okay, these points show our simulation covering factors for various halos and various projections through those halos at redshift 2 and 3. Redshift 2 are the filled symbols. This is the data for star-forming galaxies, LBGs, i.e. done by Gwen Rudy and ourselves. Okay, and that seems to agree within the rather large error bars with the predictions of these simulations. That has been interpreted as a success. Okay, and here's where the quasars land. Okay, looks pretty much like it has to be a failure. All right, there's way more cool gas in the quasars than is predicted by these simulations. Now, of course, the feedback in these simulations was mild. Now, I don't believe that this is necessarily the signature of quasar feedback. Why? Well, is this really what you want it to look like? 10 to the 11 solar masses of cool gas in the CGM? It's eventually going to form stars and you've got an even bigger cooling flow problem, right? Okay? And then, it is metal enriched, but I think that it's hard to argue that the entire CGM, the entire mass of the CGM is something ejected from an AGN. At least that makes me uncomfortable, but I'm an AGN feedback denier. Maybe quasars are special. I don't think that that's likely. I think that there's some small scale structure, some clumpiness that's essentially fundamentally not resolved or captured by these simulations. And so then another piece of evidence for that, also in the quasar environment in the little bit of time that I have left, there's this massive reservoir of cool gas, okay? And there's also a luminous quasar emitting ionizing photons. So just like in H2 region, you might expect to illuminate this gas and see a recombination cascade. And this is a simulation by Sebastiano Cantalupo, who's in the audience, using his RadMesh code showing what that might look like in terms of the 3D structure and the surface brightness. Okay, so then here's one of those pairs that I just showed you. Foreground quasar is here. This is the background quasar. You're looking at a two-dimensional spectrum. This is the strong absorption line system at the location of the foreground quasar, right? So that pinpoints where the cool gas is. I might then want to look for emission from that cool gas, okay? So then you subtract off the PSFs of the two quasars, and you smooth, and lo and behold, there is this massive, or this very large nebular structure there. So then you go to Keck, and you make a custom narrowband image, okay, at that wavelength, and you find one of the largest Lyman alpha nebulosities ever discovered. But this is not a high redshift radio galaxy or a weird system. This is just a typical radio quiet quasar, okay? So maybe this is the scaled up version of what Jay Gallagher showed us. Maybe this is what Nadia's O3 regions look like in Lyman alpha. I really don't think that's all feedback, okay? What I do think is going on, and I'll defer to Sebastiano Cantalupo about this, but basically, what I do think is going on in these systems, and we think 10% of quasars look like this, okay, is if you calculate how much mass you need to get that Lyman alpha emission, and this is of course challenging because you don't know the density, and the emission goes to the density squared, so there's an unknown clumping factor. But in order to get realistic masses, like 10 to 11 solar masses, we need clumping factors of a factor of 100 or larger, okay? So another piece of evidence that there's some kind of small-scale structure or dense clumps in the circumgalactic medium that are not being captured. I'm out of time, so I'll just leave the 3 unsolved problems there. Happy to take your questions.
So Joop's hand first.
So I totally agree that lots of the metals must be in very small
I said the H1.
Well, the metals is what you use for the ionization.
Yeah, but
right?
see, this is so we can go back to this. This is why I showed you this, right? Let's see if I can get there in time, but
the good alignment with the high order.
right. So if you, there's no way to do that and segregate metals from H1. I mean, you just I don't see how you can do that. I mean, you center on the metal lines and you get perfect alignment with the H1. So if you want to put metals on really small scales and the H1 on really large scales and do something magical such that they move the same, you can do that, but the data doesn't require that.
No, but it's actually, so it's quite natural that these little clumps, as they move out, that they will come at rest, not mixed properly, for the same density, temperature, and velocity as the environment. If you do that in a 100 parsec scale, I've done that in models, you don't see any difference in those kind of, you don't see any misalignment there, because there's no relative velocity.
Well, okay, so you can have a chocolate chip cookie model of metals, and we can call that. I just don't believe that that's necessary, and I also don't believe that you'll get this good of kinematic alignment that way.
It's what you get out naturally.
What causes the metals to be segregated in this way? It doesn't make any sense.
They come out in the clumpy way, as we see, for example, H alpha, clumpy M82, that kind of thing. If you then see what happens to them, they only have to expand a tiny bit. And since you're looking at these things over billions of years,
I don't agree that you can get this kind of kinematic alignment with a model where the metals and the H1 are not mixed. Okay, we can talk about that offline, but I don't believe that.
well, as I said, I've actually done it.
Well, publish
publish
it.
I have.
Well, I don't think you have. I don't think you have.
Thorsten Tepper Garcia's paper.
You have.
Thorsten Tepper Garcia's paper. So that may not be the correct scenario, but there is certainly
I
scenarios.
don't think it is the correct scenario.
in which-
I'd be happy to discuss this offline, but I'm really convinced that you cannot get this detailed of kinematic alignment if you have the metals in the H1 on small scales. I realize this is a bummer, dude. I mean, it's tough. Like, I mean, the clumps are small.
No,
the simulations don't have the resolution, but I mean, I think this is what it is. Like,
No, I have no trouble. I mean, I said that myself, as you know, as you said as well. But that's not in the simulations. This small scale inhomogeneity. But you have to come with arguments, not just say I don't believe.
well, this is a very, very compelling argument in signal to noise 70 data, yo.
No,
that
but-
the metals are very, very aligned with the H1.
But I just told you
That's a very
I can
compelling
reproduce
argument.
that without any velocity
I
changes.
think for both of you.
Oh, but I don't
we can take
believe
this- Joe,
well,
let's
common
calm
arguments.
down. Let's
Read the
let's-
paper.
Let's have this discussion.
Well, read this paper.
Christoph, I'd like to move on to other people. Christoph, and then Nadia.
If you do see metals there, magnetic fields must also come along, right? We know the iron is magnetized, so that if you do have a metallized environment, we have some clumps there, we get magnetic draping that completely changes the disruption time scales I showed yesterday.
I agree. It's not clear to me that you can get that idealized situation of magnetic field lines that are strong enough in one direction in the CGM. I'm just saying.
You don't need
this
so
is-
magnetic field. That's the point of magnetic draping. It's a very weak field. You just need a magnetic coherence length that is larger than a tenth of the sort of radius. So in your case, the coherence length needs to be about parsec or
Yeah, so I think that there's a big problem with why these clouds survive if there's hot plasma there, and that could very well be a solution. I mean,
Nadja and then Phil, because you're still waving your hands both of you.
You, sort of in the heat of the discussion, you didn't say anything about the radiative transfer effects for Lyman alpha.
yeah, sorry. So in the models, you mean, or in this?
Well, I mean, you know, Lyman alpha being optically thick, largely, probably, is a different animal altogether from the O3 stuff that we're doing. It would be very interesting to compare directly in emission the optically thick lines and the optically thin lines.
I think that's true. I don't think you can describe the extent of these nebulae just with scattering. I mean, I think it's just, the Lyman alpha surface brightness is a lot higher than the O3 in any model that you run. So I think it could be that your nebulae are also large, but you're not sensitive to as far out as we are. I'm not exact, I mean, do you mean in terms of the nebulosities? In what context are you worried about Lyman alpha radiative transfer?
Yeah, I'm worried about just the scattering, producing the...
I mean, the radiative transfer model that Sebastiano ran includes scattering, right? So the radiative transfer model that I showed here at the end, where we have these mass estimates that demand a large clumping, so those do include, this does include ionizing and Lyman alpha radiative transfer.
Phil, and then we're going to have to move on.
So I just wanted to say on the simulation side, I mean, I think you're completely right to point out that this is an incredibly challenging problem to resolve this small scale structure. But I'm not as pessimistic that it means we're totally screwed for other things we want to predict. I mean, there are a couple things that we can and do. One is check that, those properties that you're trying to predict, if all you care about is the star formation rate, converge.
But what does converge mean if you need 1,000 times more particles? You haven't run that simulation.
That's the point. Like, you can converge on certain large-scale properties.
Well, but
you don't resolve microphysics.
so tell me why you
Just in a
think,
numerical sense.
Phil, tell me
You're
why
gonna
you
have
think
the
you've
wrong
converged on the blob test.
The other
I mean,
thing,
no, but tell me why you think you've converged on the blob test, or maybe we
I'm
can
saying
discuss
I
that
don't
in discussion.
necessarily need to converge on the blob test for the small-scale structure in the CGM to get the integrated cooling rate over a halo correct.
But all the cold
That's-
gas is getting destroyed.
That doesn't necessarily.
Why not? The cold gas is
The second
disrupted.
thing, let me make a second point,
Fine.
which is closely related to the blob test, which is the other thing you can and do is check methods that have different errors. So you made the point that they're under-resolved, yes, but the qualitative sense of the error in a grid code and an SPH code is different. In an SPH code, if I under-resolve the blob test, I over-preserve clumps, I over-clump. In a grid code, if I do the same with an AMR code, I under-preserve the clumps. I artificially overmix them and wipe them out. So the qualitative sense of the error is opposite.
I agree with that, Phil, but what I don't agree with necessarily is that if you run a simulation at a factor of a 10 or 100 lower resolution, then you actually need to resolve a certain phenomena, then it's not necessarily clear to me that you can make really intelligent statements about what you're not capturing. And so if you talk to people that study the turbulent structure of the ISM, like Mordecai McLough, etc., they'll basically tell you that you need to get to this scale to resolve these kinds of things like, fragmentation, etc. I'm not an expert. There are other simulators in the room that could,
I've worked on that problem. And for example, if you want to know how fast a molecular cloud is contracting, you don't need to resolve almost anything of the turbulent cascade. If I want to resolve, the porosity to Lyman alpha photons, then I have to really worry that I don't capture microstructure. It depends on what you're trying to resolve. And I'm just saying some of these problems, some of the observables you're pointing to absolutely are unresolved. Some of them I think don't depend as sensitively on the microstructure as you're afraid they do.
I think we're going to have to move on now. Thanks for the active discussion. We will return to this before lunch, I am certain.